welcome to this HackPra All-Stars track here at OWASP conference. I have the pleasure to give some 15 minutes of introduction, not to the topics presented here, but more or less to the relationship between cryptography and web security. Short announcement before, there are some books on the topic here by D. Verlag. If you're interested in the breaks to have a look there, please do so. Okay, so my talk is titled Web Security Meets Cryptography. It rarely happens, so this is why I'm talking about it. There is a community for cryptography and there's a community for web security, and sometimes there are stupid ideas. I will talk about some from crypto. Sometimes crypto is broken, but it rarely affects web security, but I will present one case where it affects web security. And I'd like to talk about some novel ideas, how crypto can improve web security. So to phrase it a little bit differently, I would like to talk about misunderstandings. It wasn't really stupidity that was the origin for the proposals I will present here, but a misunderstanding what crypto can do and what it should do. Then I'd like to talk about the novel attacks on CBC, mode encryption. I think it's very interesting. We just a few weeks ago we had Kenny Patterson as a guest at Ruhr University, and he talked about his new results, Lucky 13. I think this is another step in totally breaking the CBC mode, and it works for TLS. Therefore, it affects web security directly. And if I say TLS is broken, then it's a little part of TLS. TLS is a very good cryptographic protocol, but we only make very standard use of it. So I would like to encourage you to think about novel ideas, how to make a non-standard use, better use of TLS in this case. Okay, but since I'm talking here as a speaker for HackPra All-Stars, let's give a short history of HackPra at Ruhr University Bochum. At Ruhr University we have courses, Diplom, Bachelor of Science, Master of Science since 2001. But this was very crypto heavy. So we had a lot of students that complained, we want to do some offensive stuff, we want to do some real hacking, we want to do all the practical things, and you'd only teach us crypto. So in 2007, two students came to me, Felix Gröbert and Tim Kornau. They asked me, if you organize this and if we care about it, will you be able to fund this and to take care about this in the faculty? I said yes, and so since semester 2007, we have a HackPra in Bochum. It was first focused on malware, so we had binary code analysis, I think like that. It now turned to web security, and this is a good thing because for binary security we have Thorsten Holz in Bochum, so I don't have to care about malware and things like that. Okay, and you here see the names of all the active people who contributed actively to the success of this. And one feature of HackPra is that we have international guest speakers, and this is the origin of the HackPra All-Stars. A lot of these well-known guest speakers are here today and will give you talks about latest developments in web security. Okay, but that's not my topic, so I cannot contribute to this. So short introduction of myself. Somewhere in there is me. This was 1991, Eurocrypt in Brighton. And this is a PhD student. So I'm coming from crypto, and this is the crypto community then. And this is my background. So I got my PhD in mathematics, theoretical science, 93. I'm working mostly in modern crypto and more in applied security. My first contacts to applied security were at Deutsche Telekom. I worked for 8 years there, and in PayTV and TLS client certificates, 2 big projects. Then I went for 2 years to the Georg Simon Ohm Fachhochschule in Nürnberg, And now, since 2003, I'm at Ruhr University Bochum, a chair for network and data security. So I thought about network, it's mainly TLS, and data, it's mainly XML, but more and more also HTML security. Okay. So what I want to talk about is I'm coming from the crypto community. I learned a lot about web security. Are there any connections? So first, and I'm not talking about crypto server to server because you can do anything there. It's not very interesting. You don't have any restrictions. The interesting part is browser server. So what can you do? What kind of crypto can you do between a browser and a server? There you have all the restrictions imposed by the fact that the browser is standardized and that you only have TLS there. So the three main points, the first and the third will be short, the second will be a little longer. Stupid crypto, this type of crypto can be broken by web attacks, so it doesn't really help. There are easier solutions that can be used there. These are things that are sometimes have been published some years ago, but they're still around, so I'd like to talk about them. Broken crypto, this is very novel. So it's nearly everybody, if TLS is used, a block cipher and CBC mode is used. If you don't know what CBC is, don't care, I have a nice picture I'll show later. And this CBC mode is under heavy attack. And it's only this mode, it's not the block ciphers themselves, it's only the CBC mode. And this has been extended up to TLS, and TLS is a very, very heavy target for this. And the last thing is, I'd like to encourage you to think about all the features that the TLS offers to you, not only the green extended validation certificates. This is stupid TLS. Why do we all go in this direction? TLS has much more to offer. Okay, so part one, misunderstandings. So one misunderstanding, this is it's now 13 years old paper, but it's cited very often. This was the introduction of signed cookies. So this is the idea, if I want to protect something, then I sign it, digitally sign it. And I have a quote here, so what you should do is you should hash the contents of your cookie and then append a signature to it. So why do I sign things normally? Normally, the signer signs something so that you, everybody, can verify the signature. But in this case, it's the same entity. It's the server that signs and the server that verifies. So it doesn't really make sense. And in addition, it doesn't protect against web attacks. So if you have a signed cookie, you can use a cross-site scripting attack to steal it, and then you can do the same things as with an unsigned cookie. So it doesn't really help you. You have a lot of effort, you have a lot of computing power, everything happens on your server, and it doesn't help you at all. So it's in fact, it's equivalent to choosing random numbers and putting those random numbers into a cookie, which is very, very, it's easier. These things are still some kind of popular, so it's hard to explain why signatures don't help. So I only have found one other article, 2006, so 6 years later, there was another article that really extends these ideas of signed cookies. So it doesn't help. So you don't have to sign cookies, there are better methods. Another nice thing I found is encrypted cookies. It's okay if you want to hide something, but this special use case is very interesting. It was the time when databases at web shops got hacked and credit card numbers got stolen. So the proposal from this paper is, why don't you encrypt the credit card number, put it in the cookie, and store it in the browser? So this makes things for an attacker much easier. I only have to get a cross-site scripting attack vector on the browser and then get the credit card. And again, this is the server encrypts something for itself. It's not really useful. So these are misunderstandings. So, and we always in crypto we teach the students, please specify your attack scenario before you specify your crypto, because this is not classical. Classical crypto is Enigma. You send a message over the air, and everybody can read it, and their encryption helps a lot. But in web scenarios, that's not the case. Okay, part 2, broken crypto. This is a very actual topic, CBC mode encryption. What is CBC mode? CBC mode is a way, if you have a long, clear text, and you have a block cipher typically takes 64 bits to encrypt it. If you have more than 64 bits, then you have to find a way somehow to chain the plain text to get a chained ciphertext. So CBC mode does this in the following way. I'll only talk about decryption because that's the part where the attack happens. So if I have a ciphertext and I want to decrypt it, then I take an initialization vector that is transmitted in the clear. This initialization vector, I take the first ciphertext, I use the block cipher to decrypt it. This part depends on a key. The key length may vary from 64 to 512 bit. Then there's a simple XOR with the initialization vector, and this returns the plain text. The same happens for the next ciphertext blocks, but instead of the initialization vector, I use the first ciphertext block for the second, and so on. So the interesting thing here is, if I'm only interested in one part of the ciphertext, I can simply cut this. I don't have to care about the beginning and the end. I just cut this, and it still works. And what is interesting here, I have an XOR here. I can flip bits. So in this bit flipping, I can use to learn something about the plain text. But I need something additional, and this is something that normally is available in the context of web security. I need a server that responds. And I've called this an oracle. So I need something that responds to my questions. And it either says the plain text is good or bad. And this is the main principle behind all these attacks. Maybe you've heard of padding oracle attacks. This is the thing that Rizzo and Dong were on, and Alphadan and Patterson also. It was described in 2002, theoretical, and practical attacks followed later. This is a very special type of padding, PKCS5 padding. If 5 bytes are missing, then you append 5 times the value 5. And this is a very nice thing. And the oracle is here, padding is correct, is good or bad. So I can reconstruct the bytes from the end to the beginning. Another type of attack was discovered in Bochum, not by me, but by 2 students of mine. It's character oracles. So if you have restrictions on the character set you are maybe using, then the oracle may tell you if there's a good or a bad character in your set. And this is the case for XML. And you have a very nice irregular definition what's good or bad. So you have type A and type B characters, and the oracle tells you if you have hit type B or type A character. And by flipping bits, I can navigate in this ASCII table. Okay, but coming to TLS, the novel breakthrough that Kenny Patterson and Alphadan achieved is if I have a normal TLS connection. The previous result was on DTLS, TLS over UDP. Normal TLS always cuts the connection if there's an error and gets a novel key and encrypts things differently. But the observation is, even if in each round a different key is used, this is independent of K. I can do this without considering K. So I can do this repeatedly, and it still works. And therefore, it now works for TLS. And what Patterson and Alphadan did is they used a small timing difference in the HMAC verification of TLS. So one possible attack scenario here is to decrypt HTTP-only cookies. So this can be used to decrypt HTTP-only cookies. It takes some time, but you have to position them correctly, but then you can decrypt them. So the message is, be careful about CBC. There's a lot on the way now. Okay, I'll finish with something that I hope you will be thinking of. TLS is much more than verifying a server's identity. So much more than verifying that postbank.de is really the server you want to talk to. You have client certificates. They are rarely used. But why not use a client certificate as some highly secure session cookie? It's much more secure than even HTTP-only cookies. Why not do this? Why always identify a server using all this PKA stuff? We heard a lot of PKA, and we're not sure what the NSA is able to do with server certificates and things like that. So why do we want to use PKI at all? We can get rid of that. There are proposals to get rid of this. And we have a unique fingerprint of each TLS connection. That's the finished messages. And to be more precise, this has already been standardized. The use of client certificates in a complex scenario, single sign-on scenario, was standardized by OASIS. This I will show you later. Then there is RFC 5929, which standardizes two different bindings to TLS. It's a binding to a server certificate. So if I can make the server certificate available in the browser to an application, to JavaScript code, can I do something more with that? And the other proposal in this RFC is to make the first finished message available to an application, to JavaScript in the browser, to do something more with that. So, and I'm nearly through. I just want to give a last example how this helps. So if we have the single sign-on scenario that was standardized by OASIS now 3 years ago, what does it do? Single sign-on scenario, you have a relying party. The relying party cannot authenticate the browser. It calls in for help, an identity provider, and this time the difference is we use TLS with client certificate. So this time the identity provider learns, the client certificate learns the public key of the browser. This public key is put into the SAML assertion. So this is about SAML single sign-on. It's not encrypted there, it's signed, and the SAML assertion is returned to the browser. Later, the browser connects to the relying party, transmits the SAML assertion, and this is not immediately accepted by the relying party. There's an additional check. The relying party assumes that the browser uses the same TLS connection, and this connection is identified by the client certificate. So what is done here, the client certificate is extracted by the relying party, is compared to the one contained in the SAML assertion, and only if these two match, access will be granted. What does this help us? In typical single sign-on scenarios, if we have a cross-site scripting vector at the relying party, we can simply steal the SAML assertion and use it for ourselves. This can't happen here, because this authentication token is now bound to the browser and is only valid if it's sent from this browser to the relying party, nothing else. And similar things you can do with the other bindings. So there's a lot to explore in TLS, and I think I'm through with my time. So thank you for your attention. If you have questions, we can discuss this later, or you can mail me. And now it's time for real web security. Thank you.